Good morning, everyone. In the last two lectures, we have discussed the graphical method for solving linear programming problem and considered both maximization of profit and the minimization of cost problems that occurred in a standard form. In the case of profit maximization, we discussed that the constraint inequalities are framed less than or equal to the available resources. And similarly, in the case of minimization of cost problems, we said that the constraint inequalities are framed, it is greater than or equal to the minimum requirements. That means the constraints for the maximization of problem all involved inequalities which are in the form of less than or equal to the model. Then at the same time, the constraints for the minimization problems, all the involved inequalities are greater than equal to the models. So in the linear programming problem, for which the constraints that involved both type of inequalities, which we are not discussed till now, in the case of maximization of profit, we said that the constraint inequalities are less than or equal to the concerned resources, and at the same time, in the case of a minimization of problem, we said that it is greater than or equal to the minimum requirement. Now we are going to consider the both type of inequalities, which are called mixed constraint problems. Therefore, today we will consider how to solve a linear programming problem when we have a mixed constraint that include both less than or equal to and greater than or equal to the given constraints. So consider one problem. See, a company produces two types of product X and Y. Each unit of product X require 1 unit of labor and 2 unit of raw materials, and each unit of product Y requires 2 units of labor and 1 units of raw materials. Then here the company has the total of 6 units of raw materials and 6 units of labor available. So the company have minimum production requirement to meet the demand as well. So that is the total production, that is sum of product X and Y, must be at least 1 unit. So each unit of the product X contribute, 10 units to the rupees 10. Each unit of product X contribute rupees 10 to the profit, and each unit of Y contribute rupee 15 to the profit. So the company wants to maximize the profit here while satisfying these constraints. So formulate this problem as a linear programming problem and solve graphically. So here we have a problem related to the maximization of profit, but we have number of requirements are there. That means number of constraints are given here. We will consider here, see, in the given problem, that is the company is producing two product, that is product X and product Y. So we have a two decision variable here, that is X and Y. And each unit of Y which require 2 units of labor and 1 units of the raw materials. So I am going to give here, see, the labor and raw materials are the requirements. So here for producing the product of X, it require 1 unit of labor and 2 units of raw material. So I am writing here, it is labor is 1 and raw material is equal to 2. And at the same time, producing each unit of commodity Y, it require 2 units of labor and 1 units of raw material as well. So I am going to denote here, it is 2 units of labor and 1 units of raw material which are required for producing product Y. Besides that, the given information, that is the company has the total of 6 units of raw materials and 6 units of labor are available. So this is one of the constraints, that is, see, the total available labor is 6 and the total available raw material is also 6. Now another important constraint which is given here, See, the company have minimum production requirement. That is, in order to meet the demand, that is, the total production, that is sum of X and Y, must be at least 1 unit. So I am going to write here this particular requirement, that is the sum of X and Y must be at least 1 unit. This is one of the important requirement. And besides that, what are the other information given in the problem? See, each unit of the product X contribute 10 rupees to the profit, and each unit of commodity Y contribute 15 rupees to the profit. So I am going to add here, that is the profit rate is also given. When profit per unit, that is while you are going to sell the product X, then you will get, company get 10 rupees, and from the sale of commodity Y, the company will get 15 rupees. So from this given information, what we want to do, the company wants to maximize the profit. Here the company wants to maximize the profit, and how many units of X and Y should be produced. So the problem is given here, that is company wants to maximize the profit. But there are many requirements are there, especially for the production of commodity X and Y. So we are going to frame the mathematical model, that is how to formulate a linear programming problem. First we have to identify the decision variables. Then we have to identify what are our objective function. Then we have to specify what are our constraints, then non-negativity constraint variables. So here, the first we are going to specify here what is our objective function. See, before the objective function, one more thing we should be kept in mind. We have two decision variable here. One is product X and product Y. So we are already specified that is product X and Y are the resources. That means we have a variable, decision variables are there. Now, after identifying the decision variable, the next step is to identify the objective function. In the given question, it is already said that company wants to maximize profit. So of course, the objective function here, it is maximization of profit, that is maximizing profit. So how we are going to maximizing? See, from the sale of commodity X, the rupee 10 is the profit. From the sale of commodity Y, rupee 15 is the profit. So I am going to write here, that is 10x Z is equal to maximization of profit, that is Z is equal to 10x plus 15y. This will become our objective function, that is maximizing the profit. Z is equal to 10x plus 15y. Then after identifying the objective function, the next step is to specify what are our constraints. See, from the R constraint, first we have to take care, that is one statement is given here, that is sum of X and Y must be at least 1 unit. That means the company should produce minimum of 1 unit in a per month or per day. So here it is, I am going to write, this is one of the important requirement, this is also one of the important constraint. So I am going to express this particular constraint first, that is subjected to the constraint of, X plus Y. It is at least 1 unit. So you should produce at least 1 or more than that. So I am putting here sign, it is greater than or equal to 1. This is one of the important requirement. See, the term here used, it is at least 1 unit. That's why here I am putting greater than or equal to 1. At least it should produce 1 or more than that, not less than that. So it is greater than or equal to 1. Another thing, that is availability of labor and the availability of raw material is also limited. So here the total available labor supply is 6 and total availability of the raw material is also 6. So here I am denoting these two constraints are, see, 1 unit of X and 2 unit of Y, which is required labor. So here I am writing it is X plus, that is 1 into X, which is equal to X plus 2Y, which is less than or equal to 6. Why I am putting here less than or equal to? Because it is maximum availability is 6, not more than that. So it is equal to or less than the 6. So that's why I am putting here it is less than or equal to 6. So here this is the second constraint, and the third constraint is related to the raw material. See here, for producing commodity X, 2 units of raw material is required. For producing commodity Y, 1 unit of raw material is required, and the total availability of the raw material is 6. So how we can frame the constraint here? see it will become 2x plus y which is less than or equal to 6 again here. See, maximum availability of the raw material is 6, not beyond that particular limit. So it may be less than that or equal to that. That's why I am putting here the sign, inequality sign here. It will be less than or equal to 6. See here in the constraint, we have greater than equal to and also less than equal to. Both constraints are here. That's why we are saying that in the given problem, it is an example of a linear programming problem with mixed constraint. And at the same time, we know the decision variable, that is x and y, which are greater than 0. So here maximization of profit is our objective function. We want to maximize our profit, that is z is equal to 10x plus 15y subjected to the constraint, that is x plus y which is greater than or equal to 1. Second one, it is x plus 2y which is less than or equal to 6. The third one, it is 2x plus y which is less than or equal to 6. And at the same time, we have a non-negativity constraint, that is both the decision variable are positive, that is it is greater than or equal to 0. So with this given framework, we can go for solving this given linear programming problem by using graphical method. So after formulating linear programming problem, the second step is to construct the graph and plot the constraint lines. So for that, first I am representing here graph taking commodity x along the x-axis and the commodity y along the y-axis. So in order to get the points of the constraint, in order to plot on the graph, we have to find the coordinate points of the given constraint. So first I am going to take the constraint number 1, that is constraint number 1 is equal to, that is x plus y which is greater than or equal to 1. So here I am converting this inequality sign, that is greater than or equal to 1, into the equality sign. So I can write it is x plus y is equal to 1. So if I am getting this particular equation, now I can assume that is y is equal to 0 and we want to find out x. See, if you assume y is equal to 0, then it will become, see, x plus 0 is equal to 1. Simply we can say that x is equal to 1. So when our y is equal to 0, the value of x is equal to 1. Similarly, by assuming the value of x is equal to 0, we can find the value of y as well. See here, the value of y, when assuming x is equal to 0, it will become, see, 0 plus y which is equal to 1. That means y is equal to 1. So when x is equal to 0, the value of y is equal to 1. So we have a two coordinate points of the constraint 1 we found. We are going to plot in the graph. See, I am here taking the scale that is lies between from 1 to 5. In the both axes, I have taken the scaling point that is from 0 to 5. Now, I am going to plot these particular points. See, here it is when y is equal to 0, then x is equal to 1. When x is equal to 0, y is equal to 1. So this will be the point. See, when y is equal to 0, then x is equal to 1. When x is equal to 0, then y is equal to 1. So I am going to joining these 2 points. So it will be like this. This will be this particular line, red line showing for the constraint number 1. So after plotting the first constraint, now we can go for the second constraint. See, the constraint number 2. See, which is given, that is x plus 2y which is less than or equal to 6. See, we are going to convert this inequality sign into the equality sign. So it will become x plus 2y which is equal to 6. So now we have an equation. We can solve it by assuming that y is equal to 0. What is the value of x? See, when y is equal to 0, then we are substituting the value of y is equal to 0. Then this term will become 0. Then what is remaining? It is x is equal to 6. So when value of y is equal to 0, x is equal to 6. Similarly, by assuming x is equal to 0, what is the value of y? See, it will become, assuming x is equal to 0, then it is plus 2y which is equal to 6. So y is equal to, dividing the both side of the equation by using 2, then it is 6 divided by 2 which is equal to 3. So when x is equal to 0, the value of y is equal to 3. Now we are going to plot these 2 coordinate points. So here it will become, see, one is when y is equal to 0, when x is equal to 0, what is the value of y, which is equal to 3. When y is equal to 0, then what is the value of x, which is equal to 6. Now I'm going to plot, these 2 points here by using a blue line that is joining the 3 and 6 here. So this is the line which showing for the second constraint, that is x plus 2y, which is equal to 6. Now we have one more constraint also. So I am going to take the third constraint, that is constraint number 3, which is equal to 2x plus y, which is less than or equal to 6. So again I am going to convert this inequality sign into the equality sign. So the equation will become 2x plus y is equal to 6. See, after framing the equality sign here, see, now I am going to assume that value of y is equal to 0. We are going to find the value of x. So substituting y is equal to 0, it will become 2x plus y, that is 0, which is equal to 6. So we can simply write it is 2x is equal to 6 by dividing the both side of the equation by using 2. Then it will become 6 divided by 2, which is 3. So when y is equal to 0, then the value of x is equal to 3. Similarly, while assuming the value of x is equal to 0, then what is the value of y? See, it will become, see, I am going to substitute x is equal to 0 here, then it will become 2 into 0 plus y, which is equal to 6. So it is 2 into 0, of course it is 0, then y is equal to 6. So this is the another point, that is when x is equal to 0, then the value of y is equal to 6. Now I am going to plot these 2 points again. So it will become, see, when value of x is equal to 0, value of y is equal to 6. So this will be the point. When the value of x is equal to 0, then value of y is equal to, see, when the y is equal to 0, then the value of x is equal to 3. So now I am going to join these 2 points as well. So I am drawing a particular line which is represented by using a green line, which is actually representing for the third constraint, which is equal to 2x plus y is equal to 6. Now see, these 2 lines, that means the green line and the blue line, where we have showing the constraint number 2 and 3, where both constraints are showing that it is less than or equal to 6. So we are going to identify a particular region which is known as the feasible region here. So the feasible region, see, after drawing these 3 lines here, which representing 3 types of constraints, the next step is to go for identification of the feasible region. So of course we are already defined that the feasible region is the region which is bounded by, or it is satisfied all the constraint, and all the points inside the feasible region, which is generally called a boundary of the feasible region, or at the corner of the feasible region, that satisfy all the constraint here. So see here, one of the constraint what I am showing here, see after drawing 2 lines, after drawing the 3 lines which representing 3 constraints here, the next step is to identify the feasible region here. See, the feasible region is the region that is bounded by a constraint line. So here in the constraint line, all the points inside the feasible region, or all the boundary of the feasible region, that satisfy all the constraints as well. See here, our constraint, that is 2 of our constraints are the less than equal to sign. See, the constraint number 2, that is representing by using blue line, and the third constraint, that is green line, was showing that our equality sign was, it is less than or equal to. It was less than or equal to type. So at that time, the feasible region will be below this particular line, or it will represent the left of this constraint. This will be the left of this constraint, because it was the less than or equal to sign, especially in the constraint. So that's why for these 2 lines, it will be the below or the left side of the constraint. At the same time, regarding the first constraint, that is x plus y, which is equal to 1, or it was the inequality sign was greater than or equal to. So its region will be, it is beyond this particular point or particular line. So we can say that it is the right side of the red line will be the feasible region as far as the first constraint. But at the same time, for the second and third constraint, it was less than. So its a feasible region we can represent, see, this is the feasible region. This shaded area will be considered as the feasible region here. So the feasible region here I am denoting, it is A, B, C, D. It will become the feasible region, and hence the feasible region in this case should be, see, inside both constraint, and it is outside this particular red line because it is x plus y is greater than equal to 1. So here finally the shaded area is considered as the the feasible region here. Any point inside this region or beyond this particular shaded region is called it is the feasible region, and this gives the value of x and y that satisfy all the constraint. Hence we can say that here's the feasible region are, it is A, B, C, D. These are E. These are the various possible feasible region or the corner points. So out of this feasible region, there will be one point which is considered as the optimal point. So next step is to identify the optimal solution of the given problem. So here we have an optimal solution in the sense that it will always lies at one of the vertices or the one of the corner point of the feasible region. What are the various corner point here? A, B, C, D and E. And we have to find out in each corner point what is the value of x and y. See, I am here representing various corner point, that is corner point A. At this particular point you just see the value of x is equal to 0. And what is the value of y? Which is equal to 1. So I am writing here x is equal to 0 and y is equal to 1 at the point A. Similarly, we have a point B also. See, at this particular point, the value of x is equal to 0 and the value of y is equal to 3. So I am denoting here B is equal to x is equal to 0 and y is equal to 3. Similarly, we have point C. The point C is nothing but it is an intersection point of two lines. That is, the green line and the blue line both are intersecting. That means these two constraints are intersecting at the point C. So in order to identify the value of x and y at the intersection point, that is point C, we have to solve these two equations. That is, we have a simultaneous equation with the two unknown variables, that is x and y. We have to solve simultaneously so that we will get the value of x and y. We will identify it in the upcoming slides. See, what is the remaining points? We have a point D. See, at this particular point, the value of x is equal to 3 and the value of y is equal to 0. So I am representing here x is equal to 3 and y is equal to 0. And we have the point E as well, and at this particular point the value of x is equal to 1 and the value of y is equal to 0. So at this particular point I am once again writing the point C. See, we have a one is green line, that is 2x plus y is equal to 6. And at the point C, another is blue line which is intersecting at point C. So it is x plus 2y is equal to 6. So I am going to take these two equations here. So I am going to solve these two simultaneous equations by using the elimination method in order to find out the value of x and y at the point C. So now I am going to solve these two equations in order to find out x and y at point B. So we have equation number 1, 2x plus y is equal to 6, which is equation number 1. X plus 2y is equal to 6, which is the equation number 2. Now, in order to solve this equation, I am going to use the elimination method. One of the variable, that is either x or y, we want to eliminate. Here I am going to eliminate, the value of x by multiplying, the equation number 2 into 2, so that the equation number 2 will become, see, it is 2x plus 2 into 2, which will become 4y, which is equal to 12. And this is the equation number 3. I am considering the equation number 3 and equation number 1. See, we have a coefficient of x, both are the same. So 2x and 2x is here. We are going to cancel out these two equations by subtracting the equation number 1 from the equation number 3. So 2x minus 2x will be cancelled out. 4y minus y, which will become 3y, which is equal to 12 minus 6, which is equal to 6. So we will have a 3y is equal to 6, dividing the both sides of the equation by using 3, then y is equal to 6 by 3, which is equal to 2. So when y is equal to 2, then we can substitute the value of y is equal to 2 on any one of the equation. Here we are going to substitute in the equation number 1. So equation number 1 is equal to 2x plus y is equal to 6. Substituting y is equal to 2 here, then this will become 2x plus 2, which is equal to 6. So solving for x, then it will become 2x is equal to 6 minus 2, that means we're subtracting from the both side minus 2, then it will become 6 minus 2, which is equal to 4. Dividing the both side by using 2, then x is equal to 4 divided by 2, which is equal to 2. Now the value of x is equal to 2 and the value of y is equal to 2 after solving the simultaneous equation. Now I am going to substitute here, that is at point C, the value of x is equal to 2 and the value of y is also equal to 2. Now out of these 5 corner points or 5 vertices, that is A, B, C, D and E, one of the point will be the optimal point. We have the problem which is related to the maximization of the profit. So the maximum value which will give you the optimal point. So we are going to substitute, the objective function. We are going to substitute the value of x and y on the objective function so as to identify our optimal solution. So at point A, the value of x is equal to 0 and the value of y is equal to 1. So I am going to substitute here. Then it will become 10 into 0 plus 15 into y is equal to 1. So 10 into 0, it will become 0 plus 15 into 1, which is equal to 15. So z is equal to, profit is equal to, here it is 15. Now at point B, x is equal to 0 and y is equal to 3. I am going to substitute x and y on the objective function. Then it will become z is equal to 10 into 0 plus 15 into y is equal to 3, which is 15 into 3, which is equal to 45. Similarly, at point C, x is equal to 2 and y is equal to 2. So I am substituting these two values on the objective function. Then it will become 10 into 2 plus 15 into 2, which is equal to 10 into 2, it is 20 plus 15 into 2, which is 30, 20 plus 30, which is equal to 50. Now similarly, at point D, the value of x is equal to 3 and the value of y is equal to 0. So at this particular point, if you go for substituting x is equal to 3 and y is equal to 0, then the objective function will become 10 into 3 plus 15 into 0, which is equal to 10 into 3, which is equal to 30. This term will become 0. And the last point, that is point E, substituting the value of x is equal to 1 and value of y is equal to 0, then your objective function will become 10 into 1 plus 15 into 0, which is equal to 10. So out of these, different value for the objective function, we should be kept in mind what was our objective function. It was profit maximization. Maximization profit was the objective function in the given problem. So out of these particular given values for the objective function, by substituting the value of x and y for the various corner points, we have to select only one optimal solution among the various feasible solution. That is, here the maximum value will be considered, which is equal to 50. So 50 is the maximum value that will provide you maximum profit, to the company by producing commodity x is equal to 2 unit and y is equal to 2 unit. So here our objective function was an optimal solution reached. So here our given problem is reached to the optimal solution, and this maximum profit here z is equal to, it is 50, and out of the among the various feasible solution we have the maximum value that is equal to 50. So our maximum profit is equal to 50, and at this maximum profit we want to produce the commodity x, which is equal to 2 unit. That is, number of units of commodity x is produced is equal to 2, and at the same time the value of y, that is number of unit of commodity y, is also equal to 2. So this is the solution or the optimal solution for the given problem. Here we should be kept in mind, we considered both constraint, that is greater than or equal to or less than or equal to, both constraints are considered here, and ultimately we reached to a optimal solution by considering the example of the profit maximization. So in this way we can find the solution to the linear programming problem graphically when we have a maximization of profit with mixed constraint, that is, we have both greater than equal to or less than equal to signs among the various constraints. So in the next lecture we will consider how to find the solution to the linear programming problem graphically when we have a minimization problem along with it is mixed constraint, that is greater than or equal to or less than equal to signs. So we'll see in the next lecture. Thank you.